So here's something worth thinking about as you settle in tonight. Right now, somewhere in the world, and I mean right at this very moment, there's a building going up. Somewhere in Shanghai, or Dubai, or Chicago or Lagos, a crane is swinging a steel beam through the air, dozens of stories above the street, and a crew of iron workers is waiting to catch it. They're bolting it into place in the dark, or in the early morning light, or under a sun so hot the metal burns through their gloves. And that beam, once it's connected, becomes part of a skeleton that's designed to stand for 100 years or more, to hold thousands of people, to sway in the wind without breaking, to resist earthquakes, absorb the force of hurricanes, and carry a weight so enormous that if you tried to imagine it all at once, every desk, every filing cabinet, every human body, every concrete slab on every floor, your mind would just kind of give up and round it off to a lot. And yet, it stands. That's the part that gets me. It stands, and nobody thinks twice about it. You walk into a tall building, you press the elevator button, you ride up 40 floors, and you sit down at a desk next to a window, and at no point does your brain send you a signal that says, hey, maybe we should worry about the fact that we're sitting in a chair that's floating 400 feet above the ground, held up by nothing but the cleverness of strangers. You just trust it. You trust it the way you trust the ground. But the ground is the ground. It's been there for 4.5 billion years. That building has been there since maybe 2004. Someone designed it. Someone did the math. Someone poured the concrete and welded the joints and tested the soil and decided, yes, this particular patch of earth can hold this particular impossible thing. And tonight, I want to talk about how all of that works. Every piece of it. How skyscrapers actually get built from the dirt up, and why they don't fall down, and what happens when they almost do. We're going to go slowly, because there's no rush. And honestly, the slower you go with this stuff, the more interesting it gets. Let's start where every building starts, which is not with the building at all. It starts with the ground. And I don't mean the surface. I mean what's underneath. Because here's the thing about a skyscraper. The taller it is, the more it weighs. And all of that weight has to go somewhere. It has to pass through the structure, down through the columns, and into the earth. And the earth has to be able to take it. If it can't, the building sinks. Or worse, it sinks unevenly. One side drops more than the other, and now you've got a leaning tower, and not the charming kind in Pisa. So before anyone draws a single line on a blueprint, before anyone even thinks about what the lobby's going to look like, engineers drill holes in the ground. They send down boring rigs, and boring here means drilling, not uninteresting, although I suppose if you're not into soil mechanics, it might sound that way. And they pull up samples of what's down there. Clay, sand, gravel, rock, sometimes all of them in layers. They test how much weight each layer can support. They measure the water table, which is the level below which the ground is saturated with water. They map out the geology of that specific site, sometimes to a depth of 100 feet or more, because what's happening 60 feet below the surface might be completely different from what's happening at 20 feet. This process is called a geotechnical investigation, and it's one of the most important steps in the entire project. Get it wrong, and nothing else matters. Your beautiful 70-story tower is only as good as the dirt it's sitting on. Now, humans have understood this at some level for a very long time. The Romans knew it when they built their massive structures, the Colosseum, the Pantheon, those enormous aqueducts. They paid close attention to foundations. They'd dig down until they hit solid ground, then lay thick mats of stone and concrete. Roman concrete, by the way, is a fascinating material in its own right. They mixed volcanic ash with lime and seawater, and it actually gets stronger over time, which is the opposite of what modern Portland cement does. But that's a tangent for another night. The point is, even the ancients knew that the foundation is everything. But for most of human history, buildings were relatively short. 5 stories, 6 stories, maybe 7. And there's a simple reason for that. They were made of masonry, brick, and stone. And with masonry construction, the walls aren't just walls, they're the structure. They're what holds the building up. Every floor is supported by the walls below it, and those walls have to be thick enough and strong enough to carry all the weight above them. Think about what that means as you go taller. Each floor you add puts more weight on the floors below. So the walls at the bottom have to be thicker than the walls at the top. Much thicker. If you've ever been inside an old masonry building, a church or a fortress, or one of those grand old municipal buildings from the 1800s, you might have noticed that the walls on the ground floor are absurdly thick. Sometimes 3 or 4 feet of solid brick. And that's for a building that's maybe 5 or 6 stories tall. The Monadnock building in Chicago is probably the most famous example of this, taken to its logical extreme. It was built in 1891, and it's 17 stories tall, which was extraordinary for a masonry building. The walls at the base are 6 feet thick. 6 feet of solid brick, just to hold up 17 stories. And that was basically the limit. You couldn't really go much higher with masonry alone, because the walls at the bottom would have to be so thick that there'd be no usable space inside the building. You'd just have this enormous, solid block of brick with tiny little rooms carved into it. Not exactly practical. So for centuries, the height of buildings was capped by the strength of their walls. And then, in the second half of the 1800s, two things changed that made the modern skyscraper possible. Two inventions, really, though one of them is more of a material than an invention. The first was structural steel. The second was the elevator. Let's talk about steel first, because it's the one that matters most for the structure. Iron had been used in buildings for a while. Cast iron columns were common in the mid-1800s, and they were a genuine improvement over masonry because iron is much stronger per unit of weight. You could make a slender iron column that carried the same load as a massive brick pier. But cast iron has a problem. It's brittle. It's strong in compression, meaning it handles being squeezed just fine, but it's weak in tension. Pull on it, bend it, and it can snap without warning. That's not ideal for a building that has to deal with wind loads, which push and pull on the structure in complicated ways. Steel is different. Steel is iron with a small amount of carbon mixed in, usually less than 2%. And that tiny bit of carbon changes everything. Steel is strong in both compression and tension. You can push on it, pull on it, bend it, and it responds predictably. It deforms before it breaks, which means it gives you warning. Engineers call this ductility. And it's one of the most important properties a structural material can have. A ductile material doesn't just suddenly fail. It stretches, it bends, it tells you it's in trouble before it lets go. Brittle materials, cast iron, glass, unreinforced concrete, they just snap. No warning. Ductility is what lets engineers sleep at night. Now, steel had been around for a while by the 1880s, but it was expensive. The Bessemer process, developed in the 1850s by Henry Bessemer in England, changed that. Bessemer figured out how to blow air through molten iron to burn off excess carbon, producing steel quickly and cheaply. Suddenly, you could make steel in large quantities at a price that made it practical for construction. And once you had affordable steel, the entire logic of building design changed. Here's why. With masonry, the walls are the structure. But with steel, you can build a frame, a skeleton of columns and beams, and hang the walls on it. The walls become just a skin, a barrier against wind and rain. They don't carry any load at all. This is the fundamental idea behind every skyscraper ever built, and it was revolutionary. It meant the walls could be thin. They could be made of anything: brick, terracotta, glass, eventually curtain walls of aluminum, and glass that weigh almost nothing. And because the walls didn't have to get thicker as the building got taller, there was no theoretical limit to height anymore. The structure was the frame, not the walls. The person usually credited with building the first true skyscraper, and this is debated because these things always are, is William LeBaron Jenney, an engineer and architect working in Chicago. In 1884, he designed the Home Insurance Building, a 10-story office building that used a steel and iron frame to carry the weight of the floors and the exterior walls. It wasn't all steel. It used cast iron columns and wrought iron beams in some places, and steel beams in others. But the key innovation was that the frame carried the load. The masonry walls were supported by the frame, not the other way around. They were, in a sense, just along for the ride. And you might be thinking, 10 stories? That's a skyscraper? By today's standards, it's barely a mid-rise. But in 1884, it was a different world. And more importantly, it wasn't the height that mattered. It was the method. Jenney proved that a metal frame could support a tall building, and that opened the door to everything that came after. Chicago, by the way, is not a coincidence here. The reason so much of early skyscraper history happened in Chicago has to do with a disaster. In 1871, the Great Chicago Fire burned through the city's core, destroying about 17,000 structures over 2 days. The rebuilding effort that followed was enormous, and it attracted architects and engineers from all over the country, all of them eager to try new ideas. Chicago became a laboratory for building innovation in a way that no other city was at that time. The fire also made people think seriously about fireproofing, how to protect iron and steel frames from heat, which turned out to be one of the critical challenges of tall building construction. But we'll come back to that. The other invention I mentioned, the elevator, is just as important, but for a completely different reason. The steel frame solved the structural problem. It made it physically possible to build tall. But the elevator solved the human problem. Because, think about it, who wants to walk up 20 flights of stairs? 5 stories was already pushing it for most people. Without a safe, reliable way to move people vertically, there was no point in building higher, because no one would rent the upper floors. Elisha Otis is the name most people know here, and his contribution wasn't actually inventing the elevator. Hoisting platforms had existed for centuries. What Otis did in 1854 was demonstrate a safety mechanism. He stood on a platform at the Crystal Palace exhibition in New York, had the lifting rope cut, and the platform didn't fall. His safety catch, a spring-loaded mechanism that grabbed onto the guide rails if the rope broke, meant that passenger elevators were now safe enough for regular use. It was pure showmanship, honestly. He had a guy with an axe cut the rope while he stood up there in front of a crowd. But it worked. People saw it and thought, okay, maybe I'd ride in one of those. By the 1870s and 1880s, hydraulic and then electric elevators were being installed in buildings across American cities. And suddenly, the upper floors of a building weren't a punishment, they were a premium. Higher floors meant better views, less street noise, more light. The economics of tall buildings flipped completely. The top floors went from being the least desirable to the most desirable, and that meant there was real money to be made by building higher. So you've got steel frames, and you've got elevators, and together they create the conditions for the skyscraper. But having the conditions isn't the same as having the thing itself. There were still enormous problems to solve. How to dig foundations deep enough, how to brace the frame against wind, how to get water and heat, and eventually electricity to every floor, how to fireproof the steel so it wouldn't soften and buckle in a blaze. Each of those problems has its own story, its own cast of characters, its own sequence of failures and breakthroughs. And the foundations, let's stay with the foundations for a moment, because what was happening underground in places like Chicago and New York in the 1890s and early 1900s is genuinely remarkable. Chicago sits on soft clay, thick, wet, compressible clay that extends down 60 or 70 feet in some places before you hit anything resembling solid rock. That's a nightmare for building tall, because soft clay squishes under heavy loads. It consolidates over time, which means the building settles, slowly sinking into the ground, sometimes unevenly. Some of those early Chicago buildings settled so much that their ground floors ended up below street level. The solution that engineers developed was something called a caisson. And the way they built caissons in the 1890s was both dangerous and ingenious. Imagine a large, hollow cylinder made of heavy timber or iron, open at the bottom and sealed at the top. Workers would climb down inside the cylinder, and as they dug out the clay and muck at the bottom, the whole thing would sink under its own weight, slowly descending through the soft ground. As they dug deeper, more sections were added on top, so the caisson kept growing taller even as it sank lower. The idea was to get all the way down to bedrock, or at least to a layer of hard clay firm enough to support the building's weight, and then fill the whole thing with concrete to create a massive, solid pier buried deep in the earth. Now, in Chicago, that meant going down sometimes 50, 60, even 70 feet. And the deeper you went, the worse conditions got. Water would seep in constantly. The clay was soft and unpredictable. Sometimes pockets of sand would release a rush of groundwater that could flood the work chamber in minutes. To deal with this, engineers borrowed a technique from bridge construction, the pneumatic caisson. This is where it gets really uncomfortable to think about. A pneumatic caisson works by pumping compressed air into the sealed work chamber at the bottom, and that air pressure pushes the water back, keeps the space relatively dry so workers can dig. The air pressure inside the chamber has to match the water pressure outside, which means the deeper you go, the higher the pressure. Workers would enter through an airlock, literally climbing down a shaft, passing through a sealed chamber where the pressure was gradually increased, and then stepping into this bizarre, pressurized room at the bottom of a hole in the ground, where they'd dig clay by hand or with simple tools, load it into buckets, and send it up through the shaft. The work was brutal. Shifts were short, sometimes only 2 hours, because the high-pressure air did terrible things to the human body. Workers experienced what was called caisson disease, which we now know as decompression sickness, the same thing that affects deep-sea divers. Nitrogen dissolves into your blood under high pressure, and when you return to normal pressure too quickly, it forms bubbles in your bloodstream and tissues. The symptoms ranged from joint pain. They called it the bends because workers would double over in agony, to paralysis and death. During the construction of the Brooklyn Bridge in the 1870s, Washington Roebling himself, the chief engineer, was permanently disabled by caisson disease. He spent the rest of the bridge's construction watching from his apartment window through a telescope while his wife, Emily, relayed his instructions to the work crews. That's a whole other story. But the point is that by the time Chicago's skyscraper foundations were being sunk in the 1890s, caisson disease was a known hazard. And yet the work continued because there simply wasn't another way to reach solid bearing ground beneath all that clay. In New York, the situation was different, but no less challenging. Manhattan has bedrock, good, hard Manhattan schist, and Fordham gneiss, but it's not at a uniform depth. In lower Manhattan, the bedrock is relatively close to the surface, sometimes just 20 or 30 feet down. That's one reason the earliest skyscrapers clustered there. But in Midtown, the bedrock dips away, plunging down over 100 feet in some spots before rising again. This geological quirk actually shaped the Manhattan skyline. You've probably noticed, or at least heard, that Manhattan's tallest buildings cluster in two groups, downtown and midtown, with a gap of shorter buildings in between. For decades, people assumed this was because the bedrock was too deep in the middle to make skyscrapers economical. More recent research has complicated that story. It turns out that land use patterns, zoning, and economics played bigger roles than geology. But the bedrock profile is real, and it absolutely affected how foundations were designed and how much they cost. So you've got these two great American cities, Chicago and New York, racing each other skyward in the 1890s and early 1900s. And each one is solving the foundation problem differently because the ground beneath them is fundamentally different. Chicago engineers became masters of spread foundations and caissons in clay. New York engineers got very good at drilling and blasting down to rock. And in both cities, the foundation work was the most dangerous, most expensive, most time-consuming part of the entire project. Even today, that's often still true. The part of a skyscraper you never see, the part buried underground, can account for a quarter or more of the total construction cost. But let's come up out of the ground now, because once you've got your foundations set, you need to start putting up the frame. And this is where the construction process gets into a rhythm that's almost beautiful in its efficiency. Think about what a steel-framed skyscraper actually is. It's a skeleton, a three-dimensional grid of columns and beams, bolted and riveted together, that carries all the weight. The walls don't hold anything up. They're just skin, hung on the frame like curtains, which is literally why they're called curtain walls. This was the revolutionary insight, and it changed not just how tall buildings could be, but how fast they could go up. Here's why speed matters. A steel frame can be erected much faster than masonry walls can be built. You're not laying bricks one at a time, waiting for mortar to cure. You're hoisting prefabricated steel members into place with cranes and connecting them. The steel arrives at the site already cut to length, already drilled with bolt holes, already marked with coded tags, telling the ironworkers exactly where each piece goes in the structure. It's like a giant three-dimensional puzzle, and the pieces are manufactured to fit. This prefabrication concept, making components off-site and assembling them on-site, was one of the great innovations of early skyscraper construction. And it's still the fundamental approach today. The workers who assembled these frames, the structural iron workers, were a breed apart. In the early 1900s, they worked without safety nets, without harnesses, walking along steel beams 6 inches wide, hundreds of feet in the air. The famous photographs from the construction of the Empire State Building and Rockefeller Center in the 1930s, men eating lunch on a beam, men tossing rivets to each other across open air. Those images are real, and they capture something about the sheer physical courage that went into building these structures. The casualty rates were staggering by modern standards. During the construction of the Empire State Building, which went up in an astonishing 14 months in 1930 and 1931, 5 workers were killed. That was actually considered a good safety record for the time. Other projects were far worse. And the rivets. Let's talk about rivets for a second, because they're fascinating, and most people have no idea how they worked. A rivet is basically a metal pin with a head on one end. In the early steel-framed buildings, the connections between beams and columns were made by driving hot rivets through aligned holes in the steel members. Here's how it worked on site. You had a team, usually 4 men. One man heated the rivets in a portable forge until they were cherry red, glowing hot. He'd then toss the red-hot rivet, literally throw it through the air, to a catcher who snagged it in a metal cone. The catcher placed the hot rivet through the pre-drilled holes in the steel, and a third man held a heavy bucking bar against the manufactured head on one side, while a fourth man used a pneumatic hammer to pound the other end of the rivet, mushrooming it out to form a second head. As the rivet cooled, it contracted, pulling the steel plates tightly together. The thermal contraction created a clamping force that made the joint incredibly tight. It was elegant, really, using the physics of thermal expansion to create a permanent, high-strength connection. A single large building might require hundreds of thousands of rivets. The Empire State Building used about 2.5 million of them, and every single one was heated, thrown, caught, placed, and hammered by hand. The riveting gangs developed an almost musical rhythm. The ring of the forge, the arc of the glowing rivet through the air, the staccato hammering of the pneumatic gun. You could hear a skyscraper going up from blocks away, this constant, percussive soundtrack of a building being stitched together piece by piece. Now, rivets have been almost entirely replaced by high-strength bolts and welding in modern construction. Bolts are faster to install, don't require a forge on site, and the quality is easier to inspect. Welding creates continuous connections that can be stronger than riveted joints. But for decades, rivets were the technology that held skyscrapers together. And understanding how they worked gives you a real appreciation for the craftsmanship involved. Here's the thing about a steel frame, though. Steel has a weakness that might surprise you. It doesn't burn exactly, but it doesn't need to. Steel loses about half its strength at around 600 degrees Celsius, which is well within the temperature range of a typical building fire. At those temperatures, steel beams begin to sag, columns begin to buckle, and the structure can collapse. This is not a theoretical concern. The Great Chicago Fire of 1871, which we talked about earlier as a catalyst for innovation, had already demonstrated how devastating fire could be to a city. And the early skyscraper builders knew that packing hundreds or thousands of people into a tall building with a steel frame meant that fire protection wasn't optional. It was existential. The solution they developed was fireproofing. And the basic concept is beautifully simple. You wrap the steel in something that insulates it from heat. In the earliest skyscrapers, this meant encasing every steel column and beam in terracotta tiles or concrete. The terracotta acted as a thermal barrier. Fire could rage in the building, but the steel inside its protective shell would stay cool enough to maintain its strength. If you've ever seen an old building being demolished and noticed that the steel beams are wrapped in what looks like clay tiles, that's fireproofing. It added weight, it added cost, and it took time to install, but it was absolutely essential. The critical importance of fireproofing was demonstrated again and again throughout the 20th century, sometimes in the most tragic ways. But the early engineers got this one right, mostly because they'd already lived through the consequences of getting it wrong. Chicago's building codes after the Great Fire were among the strictest in the world, and they mandated substantial fire protection for structural steel. New York followed with its own codes, and these requirements shaped the way skyscrapers were built. Every piece of structural steel had to be protected, which meant that the fireproofing was designed right into the construction sequence. You'd erect the steel, then the fireproofing crews would follow behind, floor by floor, wrapping everything before the interior. Finishes went in. But fire wasn't the only force that skyscraper engineers had to contend with. There was another one, invisible and relentless, that became more and more critical the taller buildings got: wind. And the story of how engineers learned to deal with wind loads on tall buildings is one of the most fascinating threads in all of structural engineering, because it forced them to think about buildings not as static objects, but as dynamic ones, structures that move, that flex, that sway in ways you can actually feel if you're standing on an upper floor on a gusty day. And that shift in thinking, from static to dynamic, changed everything about how tall buildings are designed. So let's talk about wind for a minute, because it's one of those forces that's easy to underestimate. Gravity is obvious, right? You can feel it. You know that a building has to hold itself up. But wind is sneaky. On a calm day, you forget it exists. And for most of human history, buildings were short and heavy enough that wind just wasn't a serious concern. A stone cathedral might weigh tens of thousands of tons. The wind pushes on it, sure, but compared to the sheer mass of all that masonry, the lateral force is negligible. The building doesn't care, but a skyscraper is a completely different animal. Think about what you're actually building. A very tall, relatively slender structure made of steel and glass. It's not a squat pyramid. It's more like a tall, thin reed sticking up out of the ground. And the taller it gets, the more wind it catches, and the more that wind wants to push it over. The force increases dramatically with height because wind speeds are much higher at 300 feet than they are at street level, where buildings and terrain create friction that slows the air down. Up high, the wind is unobstructed, and it hits the broad face of the building like a slow, continuous shove. Now, here's the thing about wind loads that makes them fundamentally different from gravity loads. Gravity pulls straight down, always, predictably. Wind pushes sideways, and it changes. It gusts. It shifts direction. It swirls around corners. And it doesn't just push on one side of the building. When wind hits a flat surface, it creates positive pressure on the windward face, but it also creates suction on the leeward side, the side facing away from the wind. So the building is being pushed and pulled at the same time. And the forces aren't steady. They fluctuate. They pulse. The building experiences what engineers call dynamic loading, forces that change over time. And this is where it gets really interesting, because a steel frame building isn't rigid. It can't be rigid. Steel is elastic, remember? That's one of its great virtues. It bends before it breaks. So when wind pushes on a tall building, the building deflects. It leans ever so slightly away from the wind. The top of a tall skyscraper might move several inches, even a foot or more, in a strong wind. And when the wind gusts and then eases, the building sways back. It oscillates. It moves like a very slow, very heavy pendulum. You've probably experienced this yourself if you've ever been in a tall building on a windy day. Maybe you noticed the water in a glass shifting slightly, or felt a subtle, almost seasick sensation. That's real movement. The building is genuinely swaying, and for the most part, that's completely fine from a structural standpoint. The steel frame can handle it. The building isn't going to fall over. But, and this is a big but, people inside the building don't like it. Human beings are remarkably sensitive to lateral motion. We can perceive accelerations that are incredibly small, especially the slow, rhythmic kind. And if the sway is noticeable enough, people get uncomfortable. They get anxious. In extreme cases, they get motion sick. So the engineering challenge with wind isn't just about preventing collapse. It's about controlling movement to the point where the occupants don't even know it's happening. The earliest skyscraper engineers dealt with wind in the simplest way they could. They made the buildings heavy, and they added diagonal bracing. If you think about a simple rectangular frame made of 4 steel members pinned at the corners, it has no resistance to lateral force at all. Push on it sideways, and it collapses into a parallelogram. It's like a picture frame with loose joints. But if you add a diagonal member, a brace running from one corner to the opposite corner, suddenly the frame is rigid. It can't deform without stretching or compressing that diagonal, and steel resists that. So the frame becomes stiff. Early skyscrapers used exactly this approach. They ran diagonal steel braces through the frames, usually hidden inside the walls. The Flatiron Building in New York, completed in 1902, used extensive wind bracing because its unusual triangular shape and its exposed location at the intersection of Broadway and Fifth Avenue made it particularly vulnerable to wind. There's a famous story, and this one's been embellished over the years, so take it with a grain of salt, about the wind effects around the Flatiron being so strong that they'd blow women's skirts up, and police officers had to shoo away the men who gathered to watch. The phrase 23 skidoo supposedly originated from cops chasing gawkers away from the building at 23rd Street. Whether that etymology is accurate is debated. But the wind effects around the building were very real. The narrow, wedge-shaped form accelerated wind around its corners in ways that made the street-level environment genuinely unpleasant. But diagonal bracing has a problem. It gets in the way. If you're running diagonal steel members through your building frame, those diagonals cut right through the spaces where you want to put doors, windows, and open floor plans. For a commercial office building, that's a serious issue. Tenants want open, flexible space. They don't want massive steel diagonals running through their offices. So engineers developed alternatives. One of the most important was the rigid frame, sometimes called a moment frame. Instead of using diagonal braces, you make the connections between the beams and columns extremely stiff, rigid enough that the joint itself resists rotation. In a pinned connection, the beam can rotate freely relative to the column. In a moment connection, The beam and column are locked together so that any force trying to rotate the joint has to bend the steel itself. This creates a frame that resists lateral loads without any diagonal members at all. The rigidity is in the joints. And here's what's clever about this. It gives you completely open floor space. No diagonals anywhere, just columns and beams, with the wind resistance built into the way they're connected. The trade-off is that moment connections are heavier, more expensive, and more complex to fabricate and erect than simple pinned connections with diagonal braces. You need more steel at the joints, bigger welds or more bolts, thicker plates. But for premium office space in Manhattan, where every square foot of rentable area translates to enormous revenue, that trade-off made perfect sense. Now, as buildings got taller through the 1920s and 30s, engineers started getting more sophisticated about wind. The great skyscraper race of that era, the Chrysler Building, the Empire State Building, 40 Wall Street, all jockeying for the title of world's tallest, pushed the engineering further and faster than ever before. And one of the key figures in this story is a man named Homer Gage. Balcom, though honestly, the real star of the structural engineering behind the Empire State Building was the firm of H.G. Balcom and Associates, working alongside the architects Shreve, Lamb, and Harmon. But the broader point is that these engineers were working at the absolute edge of what was understood about wind behavior on tall structures. They didn't have computers. They didn't have wind tunnels, at least not the kind we use today for buildings. They relied on simplified calculations, engineering judgment, and a healthy margin of safety. And that margin of safety is worth pausing on, because it's one of the most important concepts in all of structural engineering. When an engineer designs a steel column to carry a certain load, they don't design it to just barely handle that load. They design it to handle significantly more. The ratio between the actual capacity of the member and the expected load is called the factor of safety, or in modern practice, it's handled through load and resistance factors. But the idea is the same. You build in a cushion. For wind loads on early skyscrapers, engineers typically used generous safety factors, partly because they knew their understanding of wind was incomplete. They were, in a sense, using extra steel to compensate for ignorance. And it worked. Those buildings have stood for nearly a century now, through hurricanes and nor'easters, without structural failure. But there was something about wind that those early engineers didn't fully appreciate, something that wouldn't become well understood until later in the 20th century. And that's the phenomenon of vortex shedding. When wind flows around a building, it doesn't just push against the face and keep going. The airflow separates from the building's surface at the corners and forms spinning vortices, little tornadoes, essentially, that peel off alternately from one side and then the other. These vortices create alternating areas of low pressure on each side of the building, which means the building experiences a rhythmic side-to-side force perpendicular to the wind direction, not in the direction the wind is blowing, but sideways to it. And if the frequency of that vortex shedding happens to match the natural frequency of the building, the rate at which the building naturally wants to sway, you get resonance. The forces amplify. The sway grows larger and larger. This is the same principle that makes a wine glass shatter when a singer hits exactly the right note. The frequency of the sound matches the natural vibration, frequency of the glass. Energy builds up with each cycle, and eventually the glass can't take it. For buildings, the consequences are less dramatic than shattering, but the amplified sway can become deeply uncomfortable for occupants, and in extreme cases, it can cause structural fatigue or damage to cladding and interior finishes. The most famous example of vortex shedding causing problems isn't actually a building, it's a bridge. The Tacoma Narrows Bridge collapse of 1940, where a moderate wind set the bridge deck oscillating in increasingly wild undulations until it tore itself apart. The footage, if you've ever seen it, is astonishing. This massive concrete and steel bridge deck, twisting and rippling like a ribbon in the breeze, before finally breaking apart and plunging into Puget Sound. The exact mechanism is more complex than simple vortex shedding. It involved aeroelastic flutter, which is a self-exciting oscillation where the bridge's own motion changes the aerodynamic forces acting on it, creating a feedback loop. But the underlying lesson was the same one that skyscraper engineers were beginning to learn. When you build slender structures that interact with wind, you have to think about dynamics. You have to think about resonance. You have to think about the building not as a static object resisting a static push, but as a vibrating system responding to fluctuating forces. And this realization, which really crystallized in the 1950s and 60s, transformed the way tall buildings were designed. Engineers began using wind tunnel testing, placing scale models of proposed buildings in carefully controlled airflows, and measuring the forces and pressures on the model surfaces. They could simulate different wind speeds, different directions, even the turbulent effects of surrounding buildings. The pioneering work in this area came from researchers like Alan Davenport at the University of Western Ontario, who in the early 1960s established the Boundary Layer Wind Tunnel Laboratory, which became the go-to facility for testing tall building designs. Davenport developed methods for translating wind tunnel results into the actual dynamic loads a building would experience, accounting for the statistical nature of wind, the fact that you can't predict exactly what the wind will do, but you can describe it probabilistically. This was a huge leap. Before Davenport's work, engineers were essentially guessing about wind loads, using simplified code provisions that treated wind as a static pressure. After his work, they could model the real, turbulent, dynamic behavior of wind around complex building shapes. And this opened up new possibilities for design, because once you understand how wind actually behaves around a building, you can shape the building to reduce the forces. You can round the corners. You can taper the form. You can introduce setbacks or notches that disrupt vortex formation. The aerodynamic shaping of modern skyscrapers, all those tapered, twisted, sculpted towers you see in city skylines today. That's not just architecture for the sake of looking interesting. Much of it is engineering, deliberately shaped to manage wind. But even with better understanding and better shapes, the fundamental problem remains. Tall buildings sway, and people inside them feel it. And by the 1970s and 80s, as buildings pushed past 1,000 feet and toward ever more slender proportions, engineers needed new tools to control that motion. And this is where one of the most elegant solutions in all of structural engineering comes into play: the tuned mass damper. Imagine you have a building that sways at a particular natural frequency, say 1 cycle every 6 or 7 seconds. Now imagine you install, near the top of the building, a massive weight. We're talking hundreds of tons. Suspended on springs or pendulum cables, and tuned so that this weight naturally wants to swing at exactly the same frequency as the building. When the building sways to the right, the mass swings to the left, and vice versa. The inertia of the mass counteracts the building's motion, absorbing energy and reducing the amplitude of the sway. It's a beautifully simple idea. You're essentially fighting motion with motion. One of the most famous tuned mass dampers sits near the top of Taipei 101, the super tall skyscraper in Taiwan that held the title of world's tallest building from 2004 to 2010. The damper is a massive steel sphere, about 18 feet in diameter, weighing roughly 730 metric tons. It's suspended by cables from the 92nd floor and hangs down through several stories. And unlike most tuned mass dampers, which are hidden away in mechanical rooms where no one ever sees them, Taipei 101's damper is visible to visitors. You can go up and look at this enormous golden sphere hanging there, swaying gently, quietly, working to keep the building comfortable. During typhoons, the sphere can swing over a meter in any direction, soaking up the building's motion. It's one of those rare cases where the engineering is on display, where you can actually see the building's immune system at work. And Taipei 101 needed that damper, because Taiwan sits in one of the most challenging environments on Earth for tall buildings. It gets typhoons with sustained winds over 100 miles per hour. It sits on an active seismic zone. The Chi-Chi earthquake of 1999 killed over 2,000 people and was one of the most powerful earthquakes recorded in the region. So the building had to be designed for both extreme wind and extreme seismic forces, which is a particularly tricky combination because the strategies for resisting wind and resisting earthquakes can sometimes conflict with each other. A building that's very stiff resists wind well, but can attract enormous seismic forces. A building that's very flexible handles earthquakes well, but may sway too much in wind. Finding the right balance is one of the great challenges of super tall engineering in seismically active regions. And that tension between stiffness and flexibility brings us to another crucial concept in skyscraper design: the structural system itself, the overall strategy for how the building resists both gravity and lateral forces. Because as buildings got taller, engineers realized that the traditional rigid frame, columns and beams with moment connections, was becoming less and less efficient. The amount of steel you needed to make a rigid frame stiff enough for a very tall building was enormous. The steel wasn't being used efficiently. Most of it was going toward wind resistance rather than carrying gravity loads. And a brilliant engineer named Fazlur Khan, working at the firm of Skidmore, Owings and Merrill in Chicago, looked at this problem and decided to rethink the whole thing from first principles. And what Khan came up with in the 1960s would fundamentally change how we build tall buildings. It's not an exaggeration to say that most of the super tall and mega tall towers you see today owe their existence, in one way or another, to ideas that came out of this one man's mind. So let's talk about Fazlur Khan for a moment, because he's one of those engineers whose name should be as famous as any architect's, and yet most people have never heard of him. He was born in 1929 in Dhaka, which was then part of British India and is now the capital of Bangladesh. His father was a mathematics teacher, and Khan showed an extraordinary aptitude for math and physics from a very young age. He studied engineering at the University of Dhaka, then won a Fulbright scholarship to the United States in 1952, and within just 3 years, he had earned 2 master's degrees and a PhD from the University of Illinois at Urbana-Champaign. 3 years. That's almost absurd. He joined Skidmore, Owings and Merrill, SOM, in Chicago in 1955, and that's where he spent the rest of his career, and that's where he changed everything. Here's the problem Khan was staring at. By the late 1950s and early 1960s, engineers knew how to build tall buildings. They'd been doing it for decades. But there was a growing inefficiency problem that got worse the taller you went. Think about it this way. For a short building, maybe 10 or 15 stories, the structure is almost entirely about carrying gravity loads. The weight of the floors, the furniture, the people, the mechanical equipment, all of it pressing straight down. The lateral forces from wind are there, but they're manageable. You don't need much extra material to handle them. But as a building gets taller, the wind loads don't just increase. They increase dramatically. Wind pressure goes up with height because wind speeds are higher the farther you get from the ground, away from the friction of the Earth's surface. In the overturning moment, that's the tendency of the wind to tip the building over like a domino, increases with the square of the height. Double the height, and the overturning moment roughly quadruples. So the taller you go, the more of your structural material is dedicated not to holding the building up against gravity, but to keeping it from blowing over or swaying too much in the wind. Khan quantified this beautifully. He created what's sometimes called the Khan-Swinney chart, or more informally, the premium for height. He showed that for a rigid frame building, the traditional column and beam approach with moment connections, the amount of structural steel per square foot of floor area stays relatively flat up to about 10 stories. Beyond that, it starts to climb. And beyond about 40 or 50 stories, it shoots up steeply. You're paying an enormous premium in steel just to go taller. The building becomes heavier and heavier per square foot, which means more expensive. And at some point, it becomes economically irrational. You're spending so much on structure that the rentable space isn't worth enough to justify the cost. So Khan asked a deceptively simple question. What if you could change the structural system itself so that the premium for height was lower? What if you could find ways to resist lateral forces more efficiently so that the steel was doing double duty, carrying gravity loads and resisting wind at the same time? And the answer he arrived at was to move the primary lateral resistance to the outside of the building, to the perimeter, to the skin. Think about why that's clever. In a traditional rigid frame, the columns and beams are distributed throughout the interior of the floor plan. They resist lateral forces through the stiffness of their connections. But the most efficient place to resist overturning is at the greatest distance from the center of the building, at the perimeter. It's the same principle as why a hollow tube is stiffer than a solid rod of the same weight. If you take the same amount of material and push it to the outside, you get enormously more resistance to bending. A cardboard paper towel tube is surprisingly stiff, right? Way stiffer than the same amount of cardboard rolled into a solid stick. That's the tube principle, and Khan applied it to buildings. His first major realization of this idea was the DeWitt Chestnut apartment building in Chicago, completed in 1965. It was a relatively modest building, 43 stories, but it was the proof of concept. The exterior columns were closely spaced and connected by deep spandrel beams, creating a rigid tube around the perimeter of the building. The interior columns carried gravity loads, but didn't need to be part of the lateral system. The result was a dramatic reduction in the amount of steel needed compared to a conventional rigid frame of the same height. The structure was lighter, more efficient, and less expensive. But the building that really announced this idea to the world was the John Hancock Center, also in Chicago, completed in 1969. And this one, you'd recognize it instantly if you've ever been to Chicago. It's that tall, tapering, black tower with the giant X-braces on its face, 100 stories, 1,127 feet tall. And those X-braces aren't decoration. They're the structure. Khan used a system he called the truss tube, the exterior tube concept, but with massive diagonal braces crossing the faces of the building. Those diagonals carry both gravity loads and lateral loads simultaneously. When wind pushes on one face of the building, the diagonals on that face go into tension, and the diagonals on the opposite face go into compression. The forces flow through the diagonals, down to the foundations, in a beautifully direct path. There's very little wasted material. And here's what's really elegant about it. Because the diagonals are so efficient at carrying lateral loads, the columns and beams can be lighter. The whole structure uses about 30% less steel than a conventional rigid frame of the same height would have required. 30%. On a building that tall, that's thousands of tons of steel you don't have to buy, fabricate, transport, and erect. It's millions of dollars in savings. And the building is actually stiffer and performs better in wind than a heavier conventional frame would have. Less material, better performance. That's the mark of true engineering elegance. The Hancock Center was also innovative in another way. It was a mixed-use building, one of the first super tall towers to combine retail, parking, offices, and residential apartments all in one structure. The tapering shape wasn't just aerodynamic. It gave larger floor plates at the base where offices needed more space, and smaller floor plates at the top where apartments could be more intimate. Form and function working together. But Khan wasn't done. He kept pushing. His next masterpiece was the Sears Tower, now called Willis Tower, completed in 1973. And for this one, he invented yet another structural system, the bundled tube. Here's the idea. A single tube is efficient, but for a very large floor plate, the columns on the sides of the tube that are parallel to the wind direction, the flanges, in engineering terms, don't contribute as much to lateral stiffness because of something called shear lag. The forces tend to concentrate in the columns at the corners and diminish toward the middle of each face. Khan's solution was to divide the floor plan into 9 separate square tubes, bundled together like a pack of cigarettes. Each tube was 75 feet square. They shared common walls where they touched, so the interior columns did double duty. And here's the beautiful part. The tubes could be terminated at different heights. Some of the 9 tubes stop at the 50th floor, others at the 66th, others at the 90th, and 2 go all the way to the top at 110 stories. This created the distinctive stepped profile of the Sears Tower, and it also meant that the building's cross-section got smaller as it went up, reducing wind loads at the top where they're most critical. The bundled tube was extraordinarily efficient. The Sears Tower used only 33 pounds of steel per square foot of floor area. For comparison, the Empire State Building, built 40 years earlier with a conventional frame, used about 42 pounds per square foot, and it's a shorter building. Khan's structure was lighter per square foot and taller. When it was completed, the Sears Tower was the tallest building in the world at 1,451 feet, and it held that title for 25 years. Khan died young. He was only 52 when he passed away in 1982 while traveling in Saudi Arabia. He'd been working on projects there. It's one of those losses that makes you wonder what else he would have created if he'd had another 20 or 30 years. But his legacy is everywhere. The tubular concept in its various forms, framed tube, trussed tube, bundled tube, tube-in-tube, became the dominant structural strategy for tall buildings from the 1970s onward. When you look at the skyline of any major city today, you're looking at Khan's ideas made real in steel and concrete and glass. And I should mention concrete, because that's another thing Khan championed. He wasn't just a steel guy. He recognized early on that reinforced concrete had enormous potential for tall buildings, and he pushed for its use at heights that most engineers at the time considered impractical. Concrete had traditionally been seen as a material for low-rise and mid-rise construction. It's heavy, it's relatively weak in tension, and for decades, the technology for pumping it to great heights simply didn't exist. But Khan saw its advantages. It's excellent in compression. It provides natural fireproofing. It has good damping properties that reduce sway, and it can be formed into almost any shape. His One Shell Plaza in Houston, completed in 1971, was 52 stories of reinforced concrete, and at the time, it was the tallest concrete building in the world. The development of high-strength concrete in the 1970s and 1980s made Khan's vision even more practical. Normal concrete has a compressive strength of maybe 3,000 to 5,000 pounds per square inch. High-strength concrete pushed that to 10,000, then 12,000, then 15,000 psi and beyond. Today, ultra-high-performance concrete can reach compressive strengths of 20,000 pounds per square inch or more. That means you can make the columns smaller, which gives you more usable floor space, and you can go taller without the columns at the base becoming absurdly large. And this brings us to something that might surprise you about modern super-tall buildings. Many of the tallest buildings in the world today aren't pure steel structures. They're concrete, or they're composite, steel and concrete working together. The Burj Khalifa in Dubai, which at 2,717 feet is still the tallest building in the world as of now, has a reinforced concrete core and concrete and steel composite columns. The concrete core is essentially a massive vertical tube, or more precisely, a Y-shaped arrangement of walls that provides the primary lateral resistance. The concrete was pumped to extraordinary heights, over 600 meters, which required specially formulated mixes and massive pumping equipment that pushed the boundaries of what the construction industry thought was possible. And the Burj Khalifa's structural system is worth lingering on for a moment because it represents yet another evolution in how we think about tall building structures. Its designer, Bill Baker, also at SOM, the same firm where Khan spent his career, which is not a coincidence, developed what he called the buttressed core system. Imagine a central hexagonal core and then 3 wings extending outward from it, like a 3-pointed star or a Y shape. Each wing buttresses the core, stiffening it against wind from different directions. And as the building rises, the wings step back at different levels, so the cross-section gets smaller and the shape changes, which does something really clever from an aerodynamic standpoint. Because the building isn't the same shape at every height, the wind can't organize itself into those coherent vortex shedding patterns we talked about earlier. Remember how a consistent cross-section lets the wind set up a rhythmic push-pull that can amplify sway. Well, Baker's design essentially confuses the wind. At one height, the building presents a wide Y shape, and a few hundred feet higher it's narrower, and higher still, one of the wings has dropped away entirely. The wind hits a different profile depending on where it is on the building's face, and that means the vortices break up, they can't synchronize, and the overall lateral force is dramatically reduced. It's the same principle behind those aerodynamic tweaks we discussed: setbacks, chamfered corners, openings. But here, it's baked into the fundamental structural concept from the very beginning. Baker didn't bolt on an aerodynamic fix after the structure was designed. The structure is the aerodynamic fix. The form and the engineering are the same thing. And here's what's quietly remarkable about that. Bill Baker would be the first to tell you that the buttressed core concept didn't come from some flash of genius in isolation. It came from studying nature, from studying older buildings, from understanding Khan's tubular principles, and then asking what happens if you take that logic further. The Y-shaped plan is efficient because each wing acts like a buttress. Think of the flying buttresses on a Gothic cathedral, those angled stone arms that push back against the outward thrust of the vaulted ceiling. Same idea, just vertical and made of concrete. Each wing is braced by the other two through the central core, so the whole system is mutually stiffening. And because the primary material is reinforced concrete rather than steel, the building is heavy, which actually helps. Mass resists acceleration. A heavier building doesn't want to move as easily when the wind pushes on it, so the occupants feel less sway. That's one of the underappreciated advantages of concrete in super tall construction. It gives you mass for free, more or less, because you need the material for strength anyway, and the weight comes along with it. Now, pumping that concrete to the upper reaches of the Burj Khalifa was its own engineering saga. Think about what you're asking the equipment to do. You've got a pump at ground level, and you need to push a thick, heavy fluid, because that's what wet concrete is, a fluid with sand and gravel suspended in it, up through a pipe for over 2,000 feet. The pressure required is enormous, and you can't let the concrete sit still in the pipe for too long because it starts to set. And then you've got a 2,000-foot tall concrete plug that's essentially permanent. The mix design had to be incredibly precise, fluid enough to pump, but strong enough once cured. The team used a mix with very fine aggregates and specific chemical admixtures that kept the concrete workable during the long journey up the pipe while still achieving those high compressive strengths once it hardened. They also had to manage the heat generated by curing. When concrete sets, the chemical reaction produces heat. And in the Dubai climate, where ambient temperatures can exceed 120 degrees Fahrenheit, that heat buildup can cause cracking. So they mixed ice into the concrete. Literally, they replaced some of the water with ice chips and chilled the aggregates before mixing. They poured at night when it was cooler. Every batch was a carefully choreographed operation. And this is a good moment to zoom out and talk about something that doesn't get nearly enough attention when people discuss skyscrapers, which is the construction process itself. We've been talking a lot about structural systems and materials and design principles, and all of that matters enormously. But a building that can't actually be built is just a drawing. Constructability, the practical question of how you actually assemble this thing in the real world, in a real city, with real workers and real weather and real budgets, is a constraint that shapes every design decision, even if it's invisible in the finished product. Think about the Empire State Building again, that incredible pace of construction we touched on earlier, 4.5 floors a week. That wasn't just fast workers. It was a logistics system. The steel was fabricated in Pittsburgh, shipped to a staging area in New Jersey, loaded onto trucks that crossed the Hudson, arrived at the site on a precise schedule, and each piece was lifted directly from the truck to its position in the frame. They didn't stockpile steel on site because there was nowhere to put it. This is Midtown Manhattan. There's no room. So the whole operation ran like a just-in-time manufacturing line, decades before that term became famous in the auto industry. If a single delivery was late, or a single piece was fabricated to the wrong dimension, it could cascade through the entire schedule. The coordination was extraordinary, and it was managed largely with paper schedules, telephones, and experienced foremen who knew their trades inside and out. Modern skyscraper construction has its own version of this logistical puzzle, but with different tools and different challenges. Tower cranes, for instance. You've seen them on any city skyline where construction is happening. Those tall, slender cranes with a long horizontal arm, the jib, that swings loads across the site. On a skyscraper project, the crane has to grow with the building. It starts at ground level, and as the structure rises, the crane climbs. There are different ways to do this. Some cranes are external, standing beside the building and jacking themselves up on their own mast sections. Others are internal. They sit inside the building's core, typically in an elevator shaft or a void left in the floor plates, and they climb by, lifting themselves using hydraulic jacks and inserting new mast sections beneath. When the building is finished, the crane has to come down, which presents its own puzzle. Sometimes a smaller crane is brought up to disassemble the big crane, and then an even smaller crane disassembles that one, and so on, like a set of nesting dolls in reverse, until the last, smallest crane can be carried down in the elevator. And speaking of elevators, let's talk about them again. Because in a super tall building, elevators aren't just a convenience. They're a fundamental design constraint that shapes the entire building. Here's the problem. A traditional elevator has a single cab on a single rope in a single shaft, running from the ground floor to whatever floor it serves. In a 50-story building, that's manageable. But in a 100-story building, or a 160-story building like the Burj Khalifa, you need a lot of elevators to move a lot of people. And each elevator shaft takes up floor space on every single floor it passes through. If you run express elevators from the ground to the top, those shafts consume space on every floor in between, even though they're not stopping there. The higher you go, the more shafts you need, and the more of your lower floors get eaten up by elevator cores. At some point, you can end up with ground floors that are almost entirely elevator shafts, with barely any usable space left. This is sometimes called the elevator paradox of tall buildings. The taller you go, the more elevators you need. But the more elevators you add, the less floor space you have to justify the building's existence. The solution, which has been refined over decades, is the sky lobby system. Instead of running every elevator from ground to destination, you create transfer points, sky lobbies, at intermediate levels. Express elevators, sometimes double-deck cabs that serve 2 floors at once, shuttle people from the ground to a sky lobby. From the sky lobby, local elevators fan out to serve the surrounding floors. This way, the express shafts and the local shafts don't overlap for the full height of the building. The shafts are stacked rather than continuous, and you reclaim enormous amounts of floor space on the lower levels. The World Trade Center towers, completed in the early 1970s, were among the first buildings to use this sky lobby concept extensively, with sky lobbies on the 44th and 78th floors. It was a direct response to the elevator problem. Without it, the tower's floor plates would have been so riddled with shafts that they wouldn't have been economically viable. And this gets at something important about skyscrapers that's easy to overlook. They are, at their core, economic machines. Every decision, the structural system, the materials, the floor plate shape, the elevator layout, the facade, is ultimately filtered through the question of whether the building can generate enough revenue to justify its cost. The usable floor area, the net-to-gross ratio, is one of the most critical numbers in a skyscraper's pro forma. A building might be an engineering marvel, but if 40% of every floor is consumed by structure and services and circulation, the developer can't lease enough space to make the numbers work. This is why Fazlur Khan's innovations mattered so much commercially, not just structurally. By moving the lateral system to the perimeter and clearing the interior, he didn't just save steel. He gave developers more rentable square footage per floor. That's money. That's the difference between a building that gets built and one that stays on the drawing board. So when you look at a super tall building and admire its shape, its taper, its setbacks, understand that almost every one of those formal choices has a structural rationale, an aerodynamic rationale, and an economic rationale, all tangled together. The tapering form of the Burj Khalifa reduces wind load at the top where it matters most, reduces the structural material needed, and also happens to create a visually striking silhouette. But it also means the upper floors are smaller and less leasable, which is fine, because those floors are hotel rooms and private residences rather than office space, and the prestige of being that high up commands a premium per square foot that compensates for the reduced area. Every floor in a super tall building is a negotiation between physics and economics. And this negotiation plays out in the facade as well. The skin of the building, the curtain wall, which is where the engineering of a skyscraper meets the outside world. And it's worth spending some time here, because the curtain wall is one of those things that seems so simple. It's just glass and metal panels hanging on the outside of a building, right? But it's actually one of the most complex, highly engineered systems in the entire structure. And its story tells you a lot about how skyscrapers evolved from heavy, fortress-like things into the sleek, glittering towers we see today. So let's go back to that idea we talked about much earlier, the curtain wall as a concept. Remember, once you have a steel or concrete frame carrying all the loads, the exterior walls don't need to hold anything up anymore. They just need to keep the weather out and let light in. That was the revolutionary insight that came with skeletal framing in the 1880s. But for a long time, even after the structural frame took over, architects kept wrapping their buildings in heavy masonry cladding, stone, brick, terracotta. Partly out of habit, partly because that's what people expected a serious building to look like, and partly because the technology for lightweight curtain walls just wasn't there yet. Those early skyscrapers had steel bones, but still wore heavy coats. The real curtain wall, a thin, non-structural skin made primarily of glass and lightweight metal, didn't become standard until the mid-20th century. And the building that really announced its arrival, the one that made architects and engineers around the world sit up and pay attention, was the Lever House on Park Avenue in New York, completed in 1952. Designed by Skidmore, Owings and Merrill, the firm that would go on to do so many of the buildings we've already talked about, Lever House was this pristine glass and steel box that looked like nothing else on the avenue. Everything around it was clad in limestone and brick, heavy and ornate. And here was this transparent, almost weightless-looking thing. It was a revelation. And right across the street, Just a few years later, in 1958, came the Seagram building, designed by Mies van der Rohe, which took the glass curtain wall and refined it into something almost impossibly elegant. Bronze-tinted glass, bronze-clad steel mullions, every detail considered. These two buildings essentially established the visual language of the modern skyscraper. The glass tower, the crystal box, that image that's now so ubiquitous we barely notice it anymore. But here's the thing about a curtain wall. It looks simple, a flat plane of glass, but it has to do an enormous number of things simultaneously. It has to keep rain out, obviously. It has to resist wind pressure. And at the upper floors of a tall building, those wind pressures can be enormous, hundreds of pounds per square foot during a major storm. It has to insulate, keeping heat in during winter and out during summer. It has to manage thermal expansion, because on a sunny day, the south-facing panels might be 50 or 60 degrees warmer than the north-facing ones, and all those materials are expanding and contracting at different rates. It has to accommodate the movement of the building itself. Remember, a tall building sways. It shortens under gravity load as the columns compress. The floors deflect. The curtain wall has to absorb all of that movement without cracking, without breaking seals, without letting water in. And it has to do all of this while looking pristine and uniform from the street. Think about what that actually means from an engineering standpoint. The curtain wall is attached to the structural frame, typically at the edge of each floor slab. But it can't be rigidly attached because a frame is moving. So the connections have to allow for movement. Vertical movement as the building shortens, lateral movement as it sways, differential movement between adjacent floors. These connections are carefully designed with slotted holes, with flexible gaskets, with systems that let the wall panel float relative to the structure while still being securely held. It's a beautiful engineering problem, honestly. You're designing a skin that's both connected to and independent from the body it covers. And water. Water management in a curtain wall is its own entire discipline. You might think you just seal everything up tight and you're done. But it's not that simple. No seal is perfect, especially over decades of thermal cycling and UV exposure and building movement. So modern curtain walls use something called the rain screen principle, or pressure equalized design. The basic idea is that instead of relying on a single barrier to keep water out, you create a system with an outer layer that stops most of the rain, then an air cavity behind it, and then an inner layer that's the true air and water barrier. The cavity is designed so that the air pressure inside it equalizes with the wind pressure outside, which means there's no pressure differential to drive water inward through any small gaps in the outer layer. Water that does get past the outer skin simply drains down through the cavity and weeps out at the bottom. It's a system that acknowledges imperfection and designs around it, which, when you think about it, is a very engineering way to approach the problem. Now, the glass itself has come an incredibly long way. Early curtain walls used single-pane glass, just a single sheet between inside and outside. The thermal performance was terrible. Buildings hemorrhaged heat in winter and cooked in summer, and the mechanical systems had to work overtime to compensate. The energy crisis of the 1970s forced a reckoning with that. Double-glazed units, 2 panes with an insulating air gap between them, became standard. Then low emissivity coatings came along, microscopically thin metallic layers deposited on the glass surface that reflect infrared radiation. A low E coating on the inner surface of the outer pane keeps solar heat from entering in summer. A low E coating on the inner pane keeps interior heat from escaping in winter. Then, the air gap got filled with argon or krypton gas, which insulates better than plain air. Then triple glazing for extreme climates. The thermal performance of a modern curtain wall panel is maybe 5 or 6 times better than what they were using on those pioneering glass towers of the 1950s. And the coatings have gotten so sophisticated that you can tune the glass, specifying exactly how much visible light it transmits, how much solar heat it blocks, what color it appears from outside. That bluish-green tint you see on so many office towers, that's not just aesthetic. It's a specific coating engineered to balance daylighting with solar heat gain. Here's where it connects to the bigger picture. The facade of a skyscraper is typically one of the most expensive single components of the building, sometimes 15 to 25% of total construction cost, and its performance determines a huge portion of the building's ongoing energy consumption. A poorly performing curtain wall means oversized mechanical systems, higher energy bills for the life of the building, uncomfortable spaces near the perimeter. So, the facade is where architecture, structural engineering, mechanical engineering, and building physics all converge. The decisions made about the glass, the framing, the shading, the orientation, they ripple through every other system. And this brings us to something that's really shaped the most recent generation of super tall buildings: the question of sustainability, of energy performance, of how these enormous structures interact with the environment. Because for a long time, skyscrapers were unapologetic energy hogs. They were sealed glass boxes that relied entirely on mechanical systems to maintain comfort. The curtain wall was a barrier, not a mediator. But starting in the 1990s and accelerating through the 2000s, there's been a fundamental shift in how designers think about the building envelope. Double-skin facades, where you have 2 layers of glass with a ventilated cavity between them, allowing natural ventilation and buffering against wind and noise. Operable windows returning to tall buildings, something that had been almost unheard of since the advent of air conditioning. Integrated shading systems, external louvers that track the sun, even photovoltaic panels embedded in the facade itself, turning the building's skin into a power generator. The mechanical systems inside these buildings have undergone their own quiet revolution too. Think about what it takes to keep a 100-story building comfortable. You need heating, cooling, ventilation, humidity control. And you need it delivered to thousands of individual zones, because the person sitting by the south-facing window on the 60th floor has completely different needs than the person in an interior conference room on the 30th floor. The systems that do this, the chillers, the boilers, the air handling units, the ductwork, the piping, the controls, they take up an enormous amount of space. In a typical tall building, mechanical floors are interspersed throughout the height, usually every 25 to 30 floors. These are entire floors dedicated to nothing but equipment. You've probably noticed them from the outside. They're the floors with louvers or grills instead of glass, the ones that look different from the rest of the facade. Those mechanical floors are also structurally useful, by the way. They're often where the outrigger trusses or belt trusses are located, the ones that tie the core to the perimeter columns for additional stiffness. So the structural engineer and the mechanical engineer are literally sharing the same floors, their systems intertwined. And then there's water. A super tall building is basically a vertical city, and it needs water pressure at every level. But municipal water pressure only gets you up maybe 6 to 10 stories, depending on the system. Beyond that, you need pumps. And you can't just pump water from the basement to the 100th floor in one shot. The pressure at the bottom of that column of water would be immense, something like 430 pounds per square inch, which would blow out every fitting and fixture on the lower floors. So tall buildings use a zoned system, with pressure-reducing stations and brake tanks at intermediate levels, stepping the water up in stages. It's the same problem the elevator engineers face. You're fighting gravity with every vertical foot, and the solutions involve breaking the height into manageable segments. The vertical transportation of people, the movement of water, the distribution of conditioned air, the management of electrical power, the fire safety systems, the communication networks. All of these are running simultaneously through the body of the building, threaded through risers and shafts and chases, competing for space with the structure itself. A skyscraper is sometimes compared to a living organism, and it's not a bad analogy. The steel and concrete are the skeleton. The curtain wall is the skin. The elevators are the circulatory system. The mechanical systems are the lungs. The electrical system is the nervous system. And just like in a body, everything has to work together. And a failure in one system cascades into others. Which brings us to something we should talk about. Something that changed everything about how tall buildings are designed and built. Something that no discussion of skyscrapers can avoid. Fire safety. And specifically, the events that forced the engineering community to fundamentally rethink what it means to make a tall building safe. Because the history of skyscrapers is also, unavoidably, a history of learning from catastrophe. And the lessons have been. Written in steel and concrete and code, paid for in ways that are hard to think about, and absolutely essential to understand. Let's start with something that might surprise you. For most of the history of tall buildings, fire safety was treated almost as an afterthought, or at least it was handled with a kind of confidence that, in hindsight, looks dangerously naive. The basic logic went something like this. We fireproof the steel, we install sprinklers, we put in fire stairs, and we trust that the fire department will handle the rest. And for decades, that logic mostly held. Not because it was airtight, but because the fires that did break out in tall buildings tended to be contained. They'd burn through one floor, or part of one floor. The sprinklers would knock them down, or at least slow them, and firefighters would arrive and finish the job. The system worked well enough that people stopped questioning it. But there were warning signs along the way. The 1975 fire at One New York Plaza, a 50-story office tower in Lower Manhattan, burned through several floors and exposed serious problems with how fire could spread through the gaps between curtain wall panels and floor slabs. Those little spaces where the facade meets the structure. Remember how we talked about the curtain wall being a separate system, hung off the frame, designed to move independently? That independence creates gaps, and fire can exploit those gaps. The industry responded with what's called perimeter fire stopping. Mineral wool or intumescent materials stuffed into the joint between the edge of the floor slab and the inside face of the curtain wall, creating a seal that can resist fire for a rated period. It sounds simple, but getting it right on every single floor, at every single joint, across thousands of linear feet of facade, is painstaking work. And when it's done poorly, or when it's damaged during construction, or when someone runs a cable through it and doesn't reseal the penetration, you've got a pathway for fire and smoke to travel vertically through the building in ways nobody intended. The other major concern in tall buildings is smoke. Here's the thing about fire in a skyscraper. The fire itself is often survivable on the floors where it's burning, at least for a while. What kills people is smoke. And smoke in a tall building behaves in ways that are deeply counterintuitive. There's a phenomenon called stack effect, and it's worth understanding because it's always present in tall buildings, fire or no fire. Think of a skyscraper as a giant chimney. In winter, the air inside the building is warmer than the air outside, so it rises. It flows upward through every vertical shaft, every elevator hoistway, every stairwell, every mechanical chase. At the bottom of the building, air gets pulled in through doors and gaps. At the top, it pushes out. In summer, the effect reverses. This natural airflow is constant and powerful, and when there's a fire, It becomes a conveyor belt for smoke. Smoke from a fire on a lower floor can be pulled into a stairwell and pushed upward through dozens of floors in minutes, filling the very escape routes that people are trying to use. That's terrifying if you think about it. The stairs are supposed to be the safe path, and stack effect can turn them into flues. Modern tall buildings address this with pressurization systems, fans that pump fresh air into stairwells during a fire event, creating positive pressure that keeps smoke from entering. When you open a stairwell door in a pressurized building during a fire, you should feel air pushing past you into the corridor, not smoke rushing in toward you. These systems are carefully engineered because too much pressure and people can't open the doors. That's a real problem, especially for elderly or disabled occupants. Too little pressure and the smoke gets in anyway. The balance is precise, and it has to work even with multiple doors open simultaneously as hundreds of people are evacuating. And evacuation itself, that's a massive challenge in super tall buildings. Think about what it actually means to evacuate a 100-story building by stairs. Even at a steady pace, it can take over an hour. People get exhausted. Stairwells get crowded. Counterflow becomes an issue when firefighters are climbing up while occupants are coming down. After the World Trade Center attacks on September 11th, 2001, the engineering community had to confront the reality that their assumptions about evacuation had been fundamentally inadequate. The events of that day are difficult to discuss, and they deserve to be treated with the gravity they carry. What happened was unprecedented in scale. 2 aircraft striking the Twin Towers, causing massive structural damage and jet fuel-fed fires that burned at temperatures high enough to weaken the steel floor trusses. The towers had been designed to withstand the impact of an aircraft, specifically a Boeing 707, which was the largest commercial plane in common use when they were designed in the 1960s. And in fact, the structures did survive the initial impacts. Both towers stood for a significant period after being hit. The South Tower for 56 minutes, the North Tower for an hour, and 42 minutes. The collapses, when they came, were triggered not by the impact damage alone, but by the combination of impact damage and sustained, intense fire. The fireproofing on the steel floor trusses was dislodged by the impacts, exposing the steel directly to temperatures it couldn't withstand. As the trusses weakened and sagged, they pulled inward on the perimeter columns. Those closely spaced exterior columns that were the essence of the tube structure Fazlur Khan had pioneered. When enough columns buckled, the load redistributed catastrophically, and the floors above the impact zone fell onto the floors below, initiating a progressive collapse. The engineering investigations that followed, particularly the study by the National Institute of Standards and Technology, NIST, which took years and produced thousands of pages of analysis, changed building codes profoundly. The recommendations touched every system we've talked about: wider stairwells, more stairwells, a third exit stair in buildings above a certain height, hardened elevator shafts and stairwell enclosures with impact-resistant construction, better fireproofing, applied more thickly and with better adhesion to resist dislodgement, dedicated firefighter elevators with backup power and hardened shafts so emergency responders don't have to climb 80 floors on foot, improved communication systems, better floor-to-curtain wall fire stopping, and perhaps most fundamentally, a shift in philosophy from one that assumed occupants would shelter in place above a fire, which had been the standard advice for decades, to one that took seriously the possibility of full building evacuation. That shift is profound if you think about what it means for design. If you have to be able to evacuate everyone, your stairs have to be wider, your lobbies have to handle the flow, your elevators might need to be part of the evacuation strategy rather than shut down during fires as they traditionally were. Some modern super-tall buildings now incorporate evacuation elevators, specially designed with dedicated power supplies, pressurized shafts, and water protection that can move large numbers of people downward far faster than stairs. It's a complete rethinking of vertical circulation during emergencies. And here's where you see how all the systems we've been talking about interconnect. The structural engineer's decisions about column spacing affect how wide the corridors can be. The mechanical engineer's pressurization system has to coordinate with the facade engineer's air barrier. The elevator consultant's shaft layout determines where the structural engineer can place core walls. The fire engineer's smoke management strategy depends on the architect's floor plan and the curtain wall's airtightness. Nobody works in isolation. A modern super-tall building is designed by a team of dozens of specialized consultants, and the coordination among them is itself a kind of engineering. An engineering of process and information. Building information modeling, or BIM, has transformed how this coordination happens. Instead of separate sets of two-dimensional drawings that have to be cross-referenced by hand, the entire building exists as a single three-dimensional digital model, and every discipline works within it. When the mechanical engineer routes a duct, the model can automatically flag if it conflicts with a structural beam or an electrical conduit. When the structural engineer changes a column size, the architectural model updates, and the facade consultant can see immediately whether their connection details still work. It sounds straightforward, but the impact on constructability has been enormous. Clashes that used to be discovered on the job site when a pipe physically couldn't fit past a beam, requiring expensive, time-consuming rework, are now caught months before construction begins. For a super-tall building with millions of individual components, this kind of digital coordination isn't a luxury. It's the only way the thing gets built. And the construction process itself has continued to evolve in ways that would astonish the builders of the Empire State Building, even though some of the fundamentals remain eerily similar. Steel still goes up piece by piece, lifted by crane, bolted into place by ironworkers walking on beams hundreds of feet in the air. Concrete still gets pumped and poured and cured, but the precision and speed have changed. GPS-guided surveying instruments now position structural elements to within fractions of an inch. Self-climbing formwork systems allow concrete cores to rise at remarkable speed, sometimes a floor every 2 or 3 days. Prefabrication has expanded dramatically. Bathroom pods, mechanical modules, even entire facade panels arrive on site pre-assembled, ready to be lifted into place. The goal is always to move work off the critical path, to do as much as possible in a factory where conditions are controlled and efficiency is higher, and to minimize the time and labor required at height, where everything is slower, more dangerous, and more expensive. Safety on the job site has improved dramatically too, though construction remains one of the most dangerous industries in the world. The ironworkers who built the early skyscrapers worked without harnesses, without safety nets, without hard hats. The death toll was staggering. During the construction of the original World Trade Center in the late 1960s, 60 workers died. Today, a single fatality on a major project triggers investigations and can shut down work for days. Fall protection is mandatory. Safety netting surrounds the perimeter of every floor under construction. Training, certification, and oversight have all intensified. The culture has shifted from one that accepted death as the cost of building to one that treats every incident as a failure to be analyzed and prevented. It's not perfect. People still get hurt. People still die. But the trajectory is unmistakably toward greater care, greater accountability. And all of this, the engineering, the safety systems, the digital coordination, the construction logistics, comes together in buildings that are pushing into territory that would have seemed fantastical even 30 years ago. The Jeddah Tower in Saudi Arabia, if and when it's completed, is designed to exceed 1 kilometer in height, a full 1,000 meters. Think about that number for a moment. A kilometer straight up. The engineering challenges at that height involve things we've talked about. Wind, of course, and foundation loads, and concrete pumping, and elevator technology. But they also involve challenges that are almost philosophical in nature. At a kilometer tall, the building experiences meaningfully different wind speeds and temperatures at the top versus the bottom. The sun hits different faces at different times in ways that create asymmetric thermal expansion. The structure has to accommodate not just the loads we've discussed, but also the cumulative effects of creep, the slow, continuous deformation of concrete under sustained load, and differential shortening between the concrete core and the steel perimeter, which can amount to inches over the height of the building and has to be compensated for during construction by intentionally building columns slightly longer than their final intended height. But beyond the pure engineering, there's a question that hovers over every super tall project, a question that engineers think about even if they don't always say it out loud. And that question is simply this: should we? It's not a question about whether we can. We've established, over more than a century of relentless innovation, that we can build to extraordinary heights. The engineering toolkit exists. The structural systems are understood. The materials science is mature enough. The digital coordination is sophisticated enough. The construction methods are proven enough. We can pump concrete a kilometer into the sky. We can design foundations that transfer millions of tons into the earth. We can shape a building so the wind slides past it instead of tearing it apart. The question isn't capability. The question is purpose. And it's a question worth sitting with for a moment, because it tells you something important about the relationship between engineering and the world it serves. Every skyscraper ever built was built for a reason, and that reason was almost never purely technical. The home insurance building in Chicago wasn't built because William LeBaron Jenney wanted to prove that steel frames worked. It was built because somebody needed office space on a valuable piece of land, and building up was more economical than building out. The Empire State Building wasn't built to demonstrate riveting speed. It was built because John Jacob Rascob wanted to beat the Chrysler Building, and because there was money to be made renting floors in Midtown Manhattan. The Sears Tower wasn't built because Fazlur Khan dreamed up the bundled tube. It was built because Sears, Roebuck and Company needed to consolidate thousands of employees under one roof. The engineering followed the need. The brilliance of the engineering was in service of something. And that's actually one of the most beautiful things about structural engineering as a discipline. It's not abstract. It doesn't exist in a vacuum. Every beam, every column, every foundation pile, every curtain wall panel, every tuned mass damper, all of it exists because someone, somewhere, needed a building, and an engineer figured out how to make it stand up. The creativity is real. The intellectual challenge is immense, but it's always grounded in the physical world, in the needs of actual people. That's what separates engineering from pure science. Science asks how the universe works. Engineering asks what we can build with that knowledge, and for whom, and why. So when you look at the super tall towers of the 21st century, the Burj Khalifa, the Shanghai Tower, the Ping An Finance Center, the planned Jeddah Tower, it's worth asking who they serve and what they mean. And the honest answer is complicated. Some of them are genuine responses to density. In places like Hong Kong, Singapore, Manhattan, where land is scarce and expensive, building tall is a rational economic response. You get more usable floor area per square meter of ground. You concentrate people near transit, near services, near each other. There are real urbanistic benefits to height when it's done thoughtfully. But some super talls, especially the ones competing for the title of world's tallest, are driven by something else, by prestige, by national ambition, by the desire to put a city or a country on the global map. And there's nothing inherently wrong with that. Humans have always built monuments. The pyramids weren't efficient housing. Gothic cathedrals weren't the most practical way to hold a church service. But they meant something to the people who built them and the societies that sustained them. Super talls can function the same way, as symbols of aspiration, of technical achievement, of a culture's confidence in its own future. The tension arises when the symbol becomes disconnected from the substance, when a building is so tall that the upper floors are essentially unusable for conventional purposes, too expensive to condition, too remote from the ground, too buffeted by wind for comfortable occupancy. Then you start to wonder whether the height is serving the building or the building is serving the height. Engineers grapple with this quietly. They'll solve any problem you put in front of them, and they'll solve it brilliantly. But the best ones also think about whether the problem is worth solving in the first place. Here's what's interesting, though. Even the most extravagant super tall projects push the boundaries of knowledge in ways that benefit everyone. The research into wind engineering that went into the Burj Khalifa has applications in buildings a tenth its height. The concrete mix designs developed for pumping to extreme elevations improve concrete technology across the industry. The digital coordination tools refined on megaprojects become standard practice on ordinary buildings within a decade. Innovation trickles down. It always has. The lessons learned from building the Brooklyn Bridge made every subsequent suspension bridge safer and more efficient. The curtain wall technology pioneered at Lever House ended up on suburban office parks. The tuned mass damper concept proven at Citicorp Center is now used in buildings and structures worldwide. So even when a super tall seems like an exercise in excess, the engineering knowledge it generates has a way of finding its way into the everyday built environment. And that everyday built environment, that's really where the story of skyscrapers matters most. Not the record breakers, not the ones that make the news, but the thousands upon thousands of tall buildings around the world that people live in and work in and don't think twice about. The 30-story residential tower in Seoul, the 40-story office building in Sao Paulo, the 25-story hospital in Houston. These buildings use every single principle we've talked about tonight. Steel frames or concrete cores or composite structures, deep foundations bearing on rock or friction piles gripping clay, curtain walls keeping out the rain and the wind, mechanical systems zoned every 25 or 30 stories, pressurized stairwells, fireproofed steel, tuned dampers, or at least carefully calculated stiffness to keep the sway within comfortable limits. All of it, every bit of the engineering heritage we've traced, from the Monadnock building's load-bearing walls to Fazlur Khan's tubes, to Adrian Smith and Bill Baker's buttressed core. It's all present in some form in the buildings you pass every day without a second glance. And you know what? That's exactly how it should be. The highest compliment you can pay a structural engineer is to never think about their work. If you walk into a building and you don't wonder whether it's going to fall down, if you ride an elevator to the 40th floor and you don't feel the building swaying, if you sit next to a floor-to-ceiling window during a rainstorm and the glass doesn't leak and the wind doesn't howl, that means someone did their job extraordinarily well. The invisibility of good engineering is its greatest achievement. Think about what that means in terms of trust. Every morning, millions of people around the world walk into tall buildings. They don't check the foundation reports. They don't ask about the wind load calculations. They don't inspect the fireproofing on the steel beams. They just walk in, get in the elevator, go to their floor, and start their day. That trust, the same unconscious trust we talked about at the very beginning, is earned by over a century of accumulated knowledge, of failures studied and lessons learned, of codes written and revised, of engineers who spent their careers making sure the numbers were right. It's earned by the Washington Roeblings, who sacrificed their health in caissons beneath the East River, by the Fazlur Khans, who reimagined what a tall building could be, by the anonymous thousands of iron workers and concrete finishers and crane operators who built these structures with their hands, sometimes at terrible personal risk, so that the rest of us could live and work in them safely. There's something profoundly human about all of this. We are the species that builds. We look at a piece of ground and we imagine something rising from it, something that wasn't there before, something that defies the most fundamental force in the universe, gravity, through nothing more than cleverness and care and an understanding of how materials behave under load. A skyscraper is, in a very real sense, a monument to human stubbornness. Gravity says no. Wind says no. Fire says no. The earth itself says no. And engineers, one problem at a time, find ways to say yes. And they do it not through some single flash of genius, but through the slow, patient accumulation of knowledge across generations. Each generation inherits the work of the last, refines it, extends it, and passes it forward. The engineers working on the Jeddah Tower are standing on the shoulders of William LeBaron Jenney and Elisha Otis and Fazlur Khan and Leslie Robertson and every anonymous draftsperson who ever calculated a beam size at 3 in the morning. That's how engineering works. It's collaborative across time. No one person invented the skyscraper. No one person solved the problem of building tall. It was solved collectively, incrementally, over decades, by people who mostly never met each other, but who were all working on the same essential question. How do you build something tall and keep it standing? And they answered that question with steel and concrete and glass and mathematics and, above all, with an unwillingness to accept that something couldn't be done just because it hadn't been done before. So the next time you're in a city, any city, and you look up at a tall building, maybe you'll think about some of what we've talked about tonight. Maybe you'll notice the curtain wall and wonder whether it's a pressure equalized rain screen system. Maybe you'll feel the wind on your face and think about vortex shedding and tuned mass dampers. Maybe you'll glance at the base of the building and wonder what's happening 60 feet below your shoes. Whether there are caissons socketed into bedrock, or a matte foundation floating on clay, or friction piles driven down through layers of sand and silt. Maybe you'll ride an elevator and think about Elisha Otis standing on that platform at the Crystal Palace, telling the crowd to cut the rope. Or maybe you won't think about any of it. Maybe you'll just walk in, go about your day, and walk out again without a second thought. And that's fine too. That's more than fine. Because the building held you up. It kept you warm or cool. It kept the rain off your head and the wind out of your face. It did exactly what it was designed to do, so quietly and so reliably that you never had to think about it at all. That's engineering. That's what all of this, the history, the science, the materials, the failures, the breakthroughs, the human drama, that's what it all adds up to. Buildings that work, buildings that stand, buildings that let you forget they're even there. And right now, tonight, wherever you are, you're probably inside a building. The walls around you, the floor beneath you, the roof over your head. Someone designed all of it. Someone calculated the loads. Someone chose the materials. Someone figured out how to get the water to your tap and the electricity to your outlets, and the air to your lungs. Someone made sure that if a fire starts, you have a way out. Someone made sure the whole thing doesn't blow over in a storm, or shake apart in an earthquake, or sink into the ground under its own weight. You're surrounded by engineering right now, in this very moment. And it's holding you up. It's keeping you safe. It's giving you a place to rest. So let the building do its job. Let the engineer's work hold you. Let the walls be walls, the floor be solid, the roof be steady. You don't have to think about any of it anymore. You don't have to think about anything at all. The structure is sound. The loads are balanced. The foundation is firm. Everything is exactly where it's supposed to be. And so are you.